Hey, I'm Tongmeng, and I'll introduce our work PCC Proteus, where we design a congestion control scavenger for internet transport. It is fundamentally motivated by our observation that most current designs on internet congestion control treat all traffic the same and simply aimed at fair sharing among competing flows. However, with the surging amount of applications sharing the internet nowadays, congestion control without awareness of application needs may not be enough. Here we give some representative examples of internet applications. They all require network bandwidth resources to accomplish data transfer. However, users may have different timing requirements for different applications. When applications with elastic timing requirements compete with primary applications with inelastic timing, more bandwidth can be allocated to inelastic ones. So overall, users of both types are happy with their experience. For example, for system updates, even though it may induce a large volume data transfer, users may not notice if it takes longer time. Thus, aimed at such elastic timing requirements, our goal in its work is to design a congestion control scavenger. It should only go with any remaining bandwidth left by competing primary flows. And in that computation, the performance of primary traffic should be minimally impacted. To be specific, how shall we define such a scavenger? Let's look at an example. Alice and Bob are roommates, and they share the same wireless router. Now, Bob needs to download a video presentation file from a shared Google Drive folder. Since this is the only data flow under the Wi-Fi network, it should be reasonable to consume all the available bandwidth. Then, sometime later, Alice opens her laptop and starts watching YouTube. If fair sharing congestion control is the only available choice, the two flows will equally share the bandwidth. But in our case, that causes frequent video rebuffer during video streaming for Alice. Now, if Bob does not need the downloaded file in several hours, the downloading flow can actually back off and let the streaming flow take most bandwidth, so that Alice may enjoy better video quality. From the above process, we can extract the key design goals for a congestion control scavenger. First, when competing with primary flows, it should minimally impact their performance. Second, when there are only scavengers on the bottleneck, they should still attain fair and full utilization with low inflation. Furthermore, when Alice's local video buffer is almost full, the streaming flow can also switch to scavenger priority temporarily, so it gives some bandwidth back. Thus, different priorities are preferably implemented as a single protocol, so a flow can dynamically switch between them. Unfortunately, we don't have too many choices in existing literature, and LEDBAT is the main existing scavenger protocol. It tries to control the inflation below 100 milliseconds. However, it has problems with respect to all three of our design goals. First, it may be too aggressive as a scavenger. For example, we conduct dash experiments with different number of concurrent videos using the home Wi-Fi. When there is a LEDBAT flow running in the background, the dash bitrate can be reduced by 35 to 75%. So the yielding goals is not fully fulfilled. In addition, LEDBAT also does not satisfy the other design goals, which we do not go into details due to limited time. In this work, we designed Proteus, which satisfies the three design goals for a scavenger. Proteus employs a utility-based framework from PCC. Then, we design utility functions for primary and scavenger priorities and extend them to a hybrid mode for increased flexibility. In addition, to deal with network with high variance, we propose heuristics to handle non-congestion related noise. Due to limited time, I will only explain the architecture, the dedicated performance metrics for our scavenger utility, and our hybrid mode utility function. To start with, our architecture is inspired by the utility-based framework in PCC. Briefly, the sender calculates numeric utility value corresponding to different sending rates using the utility function, and changes sending rate based on the rate control algorithm so as to empirically maximize the achieved utility. In this work, we extend this framework to a modular architecture. First, we introduce a utility control module. It has a library of utility functions. Each of them is constructed from carefully selected performance metrics. According to inputs such as application requirements and QoE in real time, the utility module can determine which utility function to use and switch on the fly. All those utility functions can rely on the same rate control algorithm, which we adopt from past PCC works for now as a rate control module. In addition, our noise handling heuristics operate on the received RTT samples and the calculated performance metrics. Then, in our Scavenger utility function, we use RTT deviation as an indicator of flow commutation. RTT deviation is the standard deviation of successive RTT samples corresponding to a sending rate. It captures the dynamics of the buffer level caused by flow commutation and can signal flow commutation earlier, even when there is no consistent inflation. As shown here, when there is only a single flow on the bottleneck, buffer occupancy is relatively stable and low. Then, when a competing flow starts, it begins to probe for bandwidth, which can cause brief moments of increased buffer occupancy. This will show up as positive RTT deviation. Only after that, when the competing flow has ramped up and the bottleneck is approaching full utilization, will RTT consistently increase and then stay high. In fact, we may never reach this later phase if the competing protocol is trying to keep the buffer occupancy low. So this is the intuition for why RTT deviation gives us an earlier signal of flow commutation and make our scavenger utility function consistently yield against many primary protocols. Next, with the primary Proteus-P utility function and scavenger Proteus-S utility function, we can extend them to a hybrid mode Proteus-H, where the sender switches from primary to scavenger mode when the sending rate is increased above a threshold. Here, the application needs to set the switching threshold wisely, so Proteus-H results in good QE. As an example, we developed a dynamic thresholding strategy for ABR video. This strategy changes the threshold based on 3 conditions. By default, it will be enough if the switching threshold can deliver the maximum video bitrate smoothly. In our implementation, we set it to 1.5x the max bitrate. When the local video buffer is almost full, the threshold can be decreased, so competing flows may have more bandwidth share and better QE. Whenever rebuffering happens, that is, there are no chunks left in the buffer, the application sets a threshold to infinity to guarantee the sender stays in primary mode until the video resumes. In our evaluation, overall, we found that compared with LEDBAT, Proteus-S fulfills the yielding and performance goals much more consistently when competing with existing primary protocols and when running alone, respectively. In addition, we elaborate the network-wide benefits resulting from our hybrid mode utility, Proteus-H. The experiment setup is illustrated like this. Using an adaptive bitrate video emulator, we stream 1 4K video and 3 1080p videos on the same bottleneck using Emulab. For each run, the videos are randomly selected from a corpus. And we consider 2 cases where all video flows use Proteus-P and all use Proteus-H. These 2 figures present the average rebuffer ratio for 4K and 1080p videos under increasing bottleneck bandwidth, respectively. Under 70 Mbps bottleneck and when Proteus-P is used, the ABR algorithm fails to deliver the highest 4K bitrate, which explains the smaller rebuffer ratio in this case. And with larger bottleneck capacity, Proteus-H can lower the rebuffer ratio of both 4K and 1080p videos by up to 68% and 33% respectively. Beyond the results in our work, several possible future directions include improving noise handling, especially in highly fluctuating wireless networks, and incorporation of Proteus into other platforms like Quick and Kernel. Thank you for listening, and we welcome you to check our codes on GitHub and email me for any questions.
Perfect. Thanks, Don. So I'm going to again read out a few questions, starting with the first question is from Lloyd Brown. Lloyd is curious if scavengers would result in lowering of network usage when there is a competing L2 user. And if not, then what is the incentive for a user to adopt a scavenger transport when competing with hosts it doesn't care about?
Yep, sure. Thanks for the question. And so as long as there are competing flows and also the buffer or the bottleneck utilization is approaching full, so then we expect the scavenger to back off. And then regarding the latter part of the problem, that's actually a very good question. And we explained that in our 20-minute video using a motivation page, like who will use the scavenger. So yes, when there is multiple flows or multiple applications run by the same user on the end host, then it makes sense that user may want just some background applications to back up for higher applications quality for foreground applications. And on the other hand, when users only have one flow, and in that case, the incentives for this user to back off is from, for example, the equipment manufacturer and also the service provider, like Google in my example, that provides multiple services like Google Drive and YouTube. So in that case, the bottom line is that changing the priority of one flow for one user from a primary to scavenger should not impact this user's quality of experience. And on the other hand, by doing that, because people are sharing the internet with kind of limited bandwidth resources, so that may enable other competing users elsewhere in the world enjoy better QoE. So for example, service provider, that means possibly more revenue and more satisfactory user experience. So that's incentives for this case.
Perfect. So there are some constructive feedback coming from Lars and Anna that it would be good to look at LEDBAT++, sure. which is perhaps a good comparison point. But I'm going to stick with questions. So one of the interesting questions is, where should PCC Proteus be deployed? Is it inside the smartphones? Is it inside home routers? Or what do you see as the primary or interesting deployment scenarios?
Yep, thanks. So that's a pretty practical question. And similar to all previous PCC works, we only expect sender side changes. So in many cases, that is the server side or service provider side. And in that case, like big service providers like Google and other companies like Facebook, they can deploy this Proteus architecture, and then they knows what's the corresponding requirements for different applications, like the bit rates for YouTube and latency responsiveness for Facebook posts. And then they can adjust the relative priority accordingly. And then besides that, there is those cases that users use uplink and need to determine the priorities by themselves. So in that cases, we think first, users are still using the service, so the priority can still be communicated with the server side. And the other possibility is just let the user deploy it, but that will induce higher adaptation overhead. So we do not consider that path right now, but that's also an available choice.
Thank you, Tom. That was a very interesting talk. If you have any questions, feel free to post them on Slack and Q&A. In the meantime, I can start with one of my questions. In what you presented, like I kind of see like how you can sort of, when you have like some high priority traffic coming in, like scavenger can back off. But it's like a binary thing, right? So you have like one high priority flow and low priority scavenger. I was wondering if you're thinking of future extensions where you could support multiple levels of priority, like, could you adjust the parameters, like the loss function, such that you can support like, 3 or 4 different levels of priorities across flows using just end host mechanism?
Yeah, sure, that's definitely possible. And in fact, even with the current protocol designs, like there are more aggressively loss-based protocols like Cubic and Reno, and there are also latency-based protocols like BBR kind of, and then COPA and our PCC Vivace, and also we have the scavenger priority in PCC Proteus. So now we already have 3 different priorities. And also by tuning some parameters like the sensitivity to different signals like loss or latency changes, we could also tune the relative flexibility. And that's possible, but one concern for enable that high flexibility is that it's hard to control the relative fairness among competing flows, which you do not know the existence or which priority they have. So in that case, we may need some more elegant design. And right now, by only using two different priorities, the primary and scavenger, we already use the hybrid mode to show that it can combine with the application requirements and benefits the network-wide utility.
Yeah, so we have some more questions on Slack. One of the questions is, if the flow traffic is encrypted, how would you detect that it's a scavenger flow?
Okay, so one thing to clarify is that similar to all past PCC works, Proteus also only rely on end-to-end signals, and it only requires sender-side changes, and all the rate control decisions and the calculation of utility are based on packet reception results, which can be seen by the receiver from the received ACKs. So the senders do not proactively detect whether it's a scavenger flow or not. So, and regarding the other questions on Slack, so
let me relay them.
Yeah,
further.
sure. Yeah, sure. So
Okay.
Sender does not try to distinguish that, and it is set according to application requirements or user requirements by the sender.
Okay. So yeah, so the next question is, it seems that your primary metric to stand in for elastic cross-traffic detection is RTT variance or deviation. Mm-hmm. How sensitive is the algorithm to this measurement? And if the cross-traffic is highly reactive, then would your algorithm fail to detect it?
Yeah, so as we mentioned, because we're using RTT deviation for rate control and utility calculation, and besides that, we also have other latency-related metrics used. So we have to, we design several noise handling heuristics to tolerate non-congestion related noise, like the inherent RTT fluctuation in almost all scenarios. And also, the challenging case is when the fluctuation inherent in the network, even without full bottleneck utilization, is very high. So in that case, we find that actually most latency sensitive protocols may have impacted performance. So that, as mentioned, is a possible future work. And then another for the latter question, the cross traffic. If cross traffic is highly reactive, first, as we conduct experiments in our paper, that Proteus, the scavenger Proteus, can still back off against those reactive traffic. And second, it does not proactively detect whether the cross traffic is reactive or not.
So a related question to the RTT variance measurement. There's a question on, so does RTT deviation measurement, does it rely on accurate measurement of base RTT? And if so, how do you accurately measure base RTT?
Yeah, so we compare Proteus with LEDBAT, and LEDBAT does rely on the measurements for base RTT. And in our case, we don't look at the absolute value for RTT, we just look at the deviation. And the calculation would just, according to the received ACK samples, we calculate the per packet RTT and then calculate the standard deviation and use that as RTT deviation.
So you don't need to measure base RTT accurately, basically.
Yes, yeah. So the measured RTT could be some inflated value, but as long as there were flow computation, then there will be fluctuation in RTTs caused by those computation and cause penalty from RTT deviation.
Okay. Then another question is, how does PCC Proteus interact with AQM, active queue management schemes?
Yeah, so that could be a very interesting scenarios, and we didn't actually test the AQM cases. And another question related to this is the network path with traffic policy, where the switch will start to drop packets, and there will be minimum RTT deviation. So in that case, I think with AQM, if there is still such fluctuation or buffer level fluctuation caused by flow computation, then we could still achieve the scavenger priority. And if not, so like the flows, the isolation between flows is the isolation between different flows is very good, and there is not deviation caused by competition with other flows, then that may be some challenging cases. We didn't consider that currently.
Okay, great, thanks. So if there are other questions, please feel free to follow up on Slack.
Okay,
Thank
sure.
you, Tom.